In this lesson, we're going to take a look at factoring quadratics special cases. And why are they so special? Because they involve something called perfect squares, which you are a little bit familiar with, but you might be wondering why I've got a times table chart here. It's here just as a reference, really. But you do need to know your perfect squares. We're going to discuss that first. So a perfect square means when you take a number and multiply by itself. So I know this is a simple one, but 0 times 0 would give you 0 squared, so it's called a perfect square. And 0 times 0, as everybody knows already, is 0. And then similarly, 1 times 1 produces 1. 2 times 2 produces 4. So in your times table chart, they're easy to locate. These perfect squares can be found by just taking a look at the diagonals right here. So 0, 1, 4, 9, 16, 25, 36. Let's take a look at the entire page here. So they're all in this diagonal pattern all the way down through here. 49 is another one, 64 is another one, 81, 100, 121, and all the way down to 144. Good idea to practice this multiplication, or at least know that these are very special numbers, because this will help tremendously in your factoring skills. So that's why this is part of what I'm doing here. So you can find these online, or you can just refer to this one. But all of these numbers here that are highlighted, and more so, are going to be important doing the factoring process for what we're going to be taking a look at today. So let's do that. All right, so I already did a small little introduction to your perfect squares. So we'll do a little bit more. It's a matter of recognizing the numbers when you see them. So the 9, the 16, the 25, they are perfect squares because they can be rewritten as powers with 2 as an exponent. That's what a square is. Okay? So shouldn't be anything too shocking there. Algebraically, x squared is also a perfect square, and that's going to be important for the factoring as well. So this might seem kind of silly, but this is very important that you can rewrite algebraic expressions as powers with an exponent of 2. This one's even sneakier. So 4x squared. 4 is a perfect square, and x squared is a perfect square. So that's what you get inside the bracket. So the 2 is squared to give you the 4, and the x is squared to give you the x squared. So your perfect square is 4x squared, and it would be rewritten as 2x all to the power of 2. All right, so notice we can say that 4x squared is a perfect square, x squared is a perfect square, 9 is a perfect square, 16 is a perfect square, and the one that's missing in here is, just move that over a bit, 25. So 25 is also a perfect square. I just have to move this over just this much. There we go. All right, so it's really important to know your perfect squares to be able to tackle what we're going to be doing. So the first thing we're going to take a look at is perfect square trinomial. So that's important because a trinomial has 3 terms. So how are you going to be able to recognize these things where you're looking for specific patterns? So to do that, we're going to take a look at expanding each one of these like we did a while back in previous lessons, and seeing if we identify any patterns that can help us do the factoring part. So let's take a look at this first one here. So I've expanded this one for you, and this is just using distributive property. If you've forgotten, we'll do a quick little review. So x times x times the 2, 2 times x, 2 times 2. And that's what this line produces, x squared plus 2x plus 2x plus 4, which simplifies to x squared plus 4x plus 4. Now, if I repeat the same pattern with b, again, there's a distributive property. So again, you notice there's h times h times -3, -3 times h, and so on, and then it simplifies. The last one, same idea. So distributive property to get that pattern. So the question is there a pattern or something that's happening in each one of these? Probably best to look here. that you can readily identify how perfect squares are involved with this factoring concept. Now remember, factoring involves taking your trinomial, which is the answer in each one of these, and trying to come up with that there, your factored form. So in each one of these, take your trinomial, factor that, take your trinomial, factor to that. So the question is, what's the trick? There's got to be a trick to it, and that's what we're going to take a look at. Well, there's something special about the first terms and the constant terms. What do you think that is? We've got x squared, 4, h squared, 9, 9f squared, and a 4. Well, if you take a look at some of the samples up above, the 4 was part of a perfect square. The x squared is part of a perfect square. The 9 is also a perfect square. So these are all perfect squares. The 9, the 4, f squared, h squared, x squared, and that 4. So that's kind of interesting. So those are perfect squares. But to get these middle terms figured out, so take a look in here. So the 4x, 2x, and 2x, negative 6h, negative 3h, negative 3h, negative 12f, negative 6, and negative 6f's. So there seems to be some kind of repetition here. There's 2 of each of these terms in each one. So there's another pattern. So not only do we have perfect squares at the beginning and the end of the trinomial, but the middle part comes from a doubling of something else. So again, the middle part comes from a doubling, middle part comes from a doubling, 2 of the same terms. And that's exactly the pattern we're going to be looking for. So that the first part is a perfect square. The constant is a perfect square in each one of them. So 9, now you might be wondering why this is a negative. We'll talk about that in a second. Same thing here. Why is this negative and not positive? But they are perfect squares. So 9f squared is a perfect square because 3 squared would give you 9 and f squared gives you f squared. So the 2 in each one of these is that doubling pattern that I referred to. There's 2 of those, there's 2 of those, and there's 2 of those. So that's also part of the pattern. Now, since this was a doubling of 2x, we have 2x in there. This is a doubling of negative 3h. This is a doubling of negative 6f. So the sneaky part here, you might be wondering why there are these negatives. Why is this important? Well, the only way to get a negative 3h is to use a negative here. And you'll see that with the distributive property. Take a look. So the only way to get a repetition of negative 3h here, the constants have to be both negative. Negative 3 and negative 3 produce the positive 9. Same thing works with this one. So why are we using a negative 2 in this perfect square? Because we needed a negative, we needed 2 of these 6f's, but they had to be negative. Okay, so these 2 negatives will produce a positive, but we need them to produce the negative 6f's. Okay, so it's a little sneaky when you're dealing with negatives, but hopefully we'll get through some examples and this will clear things up. So there's 2 different types of perfect square trinomial patterns. So here's your trinomial. Let's see if you can follow the pattern. All the signs here are positive. So to get to the factored form, we use whatever was squared in this perfect square, whatever was squared in this perfect square. And we have to make sure that the middle term fits the pattern we need, that it's a doubling of the A and the B. And why do we use the positive? Well, because of the plus signs that are being used here. Same thing applies here. So to factor a squared, b squared, and having this middle term negative 2ab, notice the negative sign is now being used. So there's that doubling pattern again, but it has to be a negative doubling pattern because of the negative sign that we're going to be using in the factored form. So let's see how this works with examples. Now we're going to be starting off with trinomials, identifying what the patterns are, and if they fit, we're going to rewrite them in factored form. We will get there. So as a summary of what you've seen so far, you've seen if you're given a trinomial, the very first rule we always talk about is greatest common factor. That's your golden rule. And then the next thing you should be thinking of at this point is, does it fit a perfect square pattern? So does this fit the pattern that we've been talking about here or up here? Okay. If it doesn't, well, then we have to take a look at whether it's a simple trinomial where the a value is equal to 1. And if it is, we can use the product and sum technique. And if it's not equal to 1, that's what that statement's referring to, and it's a complex trinomial, and we have to use decomposition or sum of cross products. So this is kind of a flow to your pattern of how to factor questions, especially if you're given a trinomial. So let's get to some examples and see how this works. All right, so factoring trinomials. Let's see how this works. So because you have a trinomial, and one of the first things was look for a greatest common factor. There isn't. No x's are common, and no numbers are common other than 1, which is not helpful. So that's taken care of. Then we want to take a look at the first term and the constant term. Are they perfect squares? Well, we know x squared is a perfect square. What about 144? Yes, it is. Right there. 144 is a perfect square, and that can be written as 12 squared. So what we're trying to do now is check to see if this thing fits the perfect square pattern. So we know that 12 squared will give us 144, x squared gives us x squared. But if I use the x and the 12 in this doubling pattern, do I get the 24x? 2 times 12 is 24, x and positive, that does work. So this does fit a perfect square pattern. That will allow us to then write the perfect square using the x here and the 12 there. And why the plus sign? Well, because the plus sign was used here in that doubling pattern. Now, eventually this step here, most students, once you get to grade 11, hopefully you don't need to write this down, but I would suggest you include it for now. All right, let's try B. Let's take a look at this one here. If I can get this to work, there we go. So once again, we're checking the pattern. So this is a perfect square. We can square the letter C and get C squared. 81 is 9 squared. Now, why is it negative? Why are we testing the negative? Well, we're testing the negative because of this negative sign in there. Because we want to try to match this with a doubling pattern of the letter C and the negative 9. So notice we still have the plus sign. So why are we using the negative? We're going to test to see if this works. We're going to use the negative 9 and the C, double that, and see if we get negative 18C. Well, 2 times negative 9 is negative 18 times a C, and that works. Since it works, we can use the C from here and the negative 9 here to produce our factored form. Okay. So notice the factored form is just one set of brackets with an exponent of 2. Right? That's the pattern. Let's try that again with another one here. All right, so again, we have the pattern that we're trying to look for is this a perfect square? Well, let's back up a bit. We almost forgot about our golden rule. Is there a common factor? That's divisible by 2 and 4. This is divisible by 2 and 4. Not an even number. That's not divisible by 2 or 4. So likely there's no common factor. So good we check that. So is this a perfect square? Well, yes, it is. 4 is a perfect square, and it's definitely x squared is a perfect square. Is 121 a perfect square? Now that's somewhat challenging, but again, you can always refer to the times table if you have to. There it is there. 121 happens to be 11 times 11. So it does fit. That's a perfect square, and that's a perfect square, but we need to check this middle part, see if it fits that doubling pattern. So once again, we're going to check. So we know that 2 squared will give us 4. X squared will give us x squared. So we know that 2x all squared is part of the pattern that we're going to use. The 121, why are we using 11? Well, or negative 11, again, because we have a negative sign here with the middle term. So we're going to test the negative 11 and square that. That'll still give us a positive 121. So we're going to use the negative 11 and the 2x and double it. There's the doubling pattern, and see if we get negative 144, or sorry, negative 44x. 2 times 2 is 4, times negative 11 is 44 with the x. That does work. Since it fits the pattern, we can go ahead and use the 2x and the negative 11 to write the factored form. Okay, now, just in saying something, if this pattern seems to be a lot for you to remember, there's nothing wrong with you just saying, well, this is a trinomial, a value is 1. I'm going to treat it as a simple trinomial, find 2 numbers and multiply to 144 and add to 24. This is a simple trinomial. I'm looking for 2 numbers that multiply to 81 and add to negative 18. This is a complex, you're going to have to use decomposition or sum of cross products, or bottoms up, whichever you like. Nothing wrong with that at all. This entire technique is designed to help you get through advanced questions in higher level math, especially if you're considering taking a university level math in grade 11. So to get through another example here. Here, again, we have that 4x squared, much like the previous one, so we can write it as 2x. The 49, that 49 is a perfect square, 7 times 7, but we're going to use negative because of the negative sign here. And we're going to check the pattern. So we're going to try to double the 2x and double the negative 7. Oops, negative 7 there. And see if we get negative 14. Well, 2 times 2 is 4 times negative 7. That is not going to give us negative 14. No way. So maybe a little stumped here. So can we try some other factoring technique? You can, but what you're going to find, if it doesn't fit this pattern, and we know it doesn't, that cannot be factored. And that is quite possible. So that could be an answer to some of your questions, that it's not factorable at all. So that is another little sneaky aspect. So you can try using decomposition or sum of cross products and try to factor it, but you're going to be spending a lot of time trying to get the answer because you're not going to find it. All right, what about in B? Now, oh, look at that. We forgot our golden rule. That's not a perfect square, neither is that. But we factor out a common 3. 3 goes into 27, 3 goes into 18, 3 goes into 3. We now have a greatest common factor and a trinomial that maybe we can factor. So this trinomial, again, you can use decomposition or sum of cross products since the a value is not equal to 1. We're going to try to fit the perfect square pattern because 9 is a perfect square and so is 1. And then we're going to use that negative sign to help us out. And this is a little bit quicker. So 3x all squared will give us 9x squared. Instead of a 1 times 1, we're going to use negative 1 times 1 and see how that works. Now, we have 3x times negative 1. That gives us negative 3x. If we double it, you do get negative 6x. So it does fit the perfect square pattern. So even though I didn't write it out, this fits the pattern that we're looking for. And we get a binomial squared. Okay. And this last one over here, similarly, it does have a greatest common factor of 5. 5 goes into each one of these evenly. And then, oh, look at that. There's the 4x squared. You should recognize that by now. 25 is definitely a perfect square. So when we test this pattern, we're going to be using 2x and positive 5. Why positive? Because that sign's positive. So 2x times the 5 gives us 10. But then we want to double that. 10 gives us 20x. So it does fit the pattern. So we want to use the 2x that came from that pattern there and the positive 5 that came from there. So again, I'm skipping that middle step as I've drawn in these previous ones. See if you can do that yourself, because that is a very good skill for moving forward in different progress or processes. So I did do a little check here for you just to make sure. Okay, but that's another way you can show your work, just to prove to yourself that it does work. Okay, so this does equal negative 6x. A little check mark there. Maybe we'll change the pen and make it a little bit more confident. Okay. All right, so that takes care of a perfect square trinomial. Now, there are more patterns, which you're probably thinking, boy, oh boy, this is getting really complicated, which it is. Unfortunately, factoring is a very complex process, but very crucial to getting through higher level math courses. So now there's going to be something called a difference of squares. Now, a difference of squares, let's go back right to the beginning. So think of it this way. If I wanted to take a 9 and a 4, and I wanted the difference between them, what operation would you use? What does difference imply? If you said subtraction, you are correct. So the difference between 9 and 4. So this is a difference of perfect squares. This can be written as 3 squared, take away 2 squared. So this is a different type of pattern that we're going to see in a moment. Actually, and we're going to take a look at the patterning that exists here with this factoring. All right, so a perfect square trinomial, I've got to get back here, sorry. So we're going to take a look at these patterns. Oops, sorry, got to get it on the right page. Difference of squares, there we are. Okay. So now we're going to take a look at recognizing some patterns here, just like we did before. Now look at the setup of the algebra. You may notice something very interesting here. Take a look at the bracketed part here and here, and then compare with this one here. Notice what the only difference is. That's right. The only difference in the bracketed part is the operation. One is a minus, one is a plus. The order doesn't matter. The plus could have come first and then the minus. But in both situations, watch what happens here. So again, using distributive property, looks like we have that doubling pattern, but it's not really doubling. The reason why it's not doubling is this one's a plus, this one's a minus. This one's a plus, this one's a minus. If we take 2x, take away 2x, that gives us 0. We have 3h, take away 3h, that also gives us 0. That doesn't double anything. That actually produces a 0, leaving behind x squared and the minus 4, h squared minus the 9, and hence the name of the pattern, difference of squares. 4 is a perfect square, came from multiplying the 2's together. 9 is a perfect square, came from multiplying the 3's together. The minus sign is as a result of the fact that the operations in the brackets are opposite. So this pattern can be written this way. X squared is a perfect square, 4 is a perfect square, h squared is a perfect square, 9 is a perfect square. So there's your difference of one squared and another squared. So the word difference means subtraction. You have a perfect square here and a perfect square there. And same thing's true here. Perfect square with a difference between them. So this pattern, if you see this exists, then that'll allow you to factor into this special format. So that gives us kind of a new property. So we're going to take a look at some other examples just to make sure this works with more complex things. using the same pattern. So again, the bracketed part, identical, except for the signs are opposite. So a quick way of getting to the answer would be take the first item, square it, take the second item, square it, put a minus sign in between. Same thing in B. You have exactly the same except for these signs. So take the 3F and square it, take the 2 and square it, put a minus sign in between. So we're expanding here, not factoring yet. Again, here in the bracketed part, the opposite signs appear. So we can take the 2y and square that. Now 2y squared, 2 times 2 is 4, y times y is y squared. There's the difference, or the subtraction. Where is the 64 coming from? Well, 8 times 8 is 64, z times z is z squared. So the third one was done a little bit quicker than the first two. Okay, but again, now we're going to be taking a look at factoring, going from here to here. What we were doing in this example is expanding just to make sure that this pattern still works, or can be used with expanding as well. Okay, so expanding involves a process of going this way, taking factored form and writing it as an expanded format. Factoring says, well, take the expanded format and write it in a factored form with brackets. This is a special pattern, difference of squares. The name is because of the expanded form, because you have two perfect squares and a difference between them. All right, so we're going to try to factor now with a difference of squares pattern. So we're going to take a look at each one of these and we'll see what the results are. So in part A, c squared is definitely a perfect square. That's c times c. 81 is 9 times 9 with a difference between. So this does fit this pattern. So I should be able to write it in this format. So let's take a look. So we have the c squared and the 9 squared. So let's take a look at how this works. So now we have the c being used here and here, and the 9 being used there and there. So it's a difference of squares pattern that factors to this step here. So these are two factors written in brackets, as you can see. Okay, so we're taking this pattern up at the top and writing it that way. And we'll see hopefully the same thing appear in this next one. So again, here we have the 4x squared, as we've seen before, it can be rewritten as 2x all squared, as it's a perfect square. We've seen 121 written as 11 squared, and difference in between them. Now, one thing you should notice as well is this pattern, difference of squares, you always have a binomial. There is no trinomial. So that is a very huge clue. Take a look. You have two terms, two terms, two terms. That is not a trinomial. So unlike the other pattern that we looked at earlier, this pattern should be easier to recognize if it exists. Okay, so again, once we find that this pattern works, we can write it in factored form. One set of brackets will have the 2x minus the 11, and the other set will have the 2x plus the 11. So let's take a look here. 9 is a perfect square, and so is x, so that could probably be 3x all squared. 5 is not a perfect square. So that's interesting. If 5 is not a perfect square, what happens here? Well, much like that previous question, it's not factorable. It's not a trinomial, you can't use any of those techniques. It doesn't fit the difference of squares pattern, so you can't factor it. And that happens from time to time. Can be done later on, just not on the grade 10 course. Okay, so just to take a look at a few other examples. Now, one thing we might have forgotten about, so 3 is not a perfect square, and 192 doesn't seem like it. Now, if you want to test with a calculator, you can always take the square root of these things. That's another way of testing to see if things are perfect squares or not. If you get a number that's not a decimal, then the number you started with was a perfect square. But we also have to remember our golden rule of common factoring. So we can take out a 3 here, and look what it leaves behind. A nice x squared, which is a perfect square, and a 64, which is a perfect square. Two terms that have a subtraction between. We've got a difference of squares. And since the x squared is coming from x times x, and the 64 is coming from 8 times 8, we now have our factored form using the above pattern. So again, difference of squares produces two factors that are identical with the opposite signs. Again, here 18 is not a perfect square, neither is 32, but maybe there's a common factor. Let's have a look, and yes, there is. There is a common factor of 2, leaving 9m squared and 16 with a difference in between. So two terms in here that are perfect squares. There's your perfect square pattern for the 9m squared minus 16. 3m coming from the 9m squared and the 4 coming from the 16 to produce these two separate factors. And just a couple more just to quickly get through here, and we'll wrap this up. A little sneaky here, 225 is actually a perfect square. And you might say, whoa, this c to the power of 4, that's interesting. Well, the 225 is 15 squared. The c to the power of 4 is c squared squared. Remember your power laws. So these two put together will give you 4. 1 is definitely a perfect square. So that does fit a difference of squares pattern. Two terms, perfect squares being subtracted. And there's your factored form. A little sneaky. Same thing's true with this one here. So again, even though it's a little bit more complex, 81 is coming from 9 squared. X to the power of 4, kind of like what we saw here, can be written as x squared. All of that is squared. So if we square a 9, we get 81. We square x squared, we get x to the power of 4. Here, 25 is coming from 5 squared. And the y squared is from the y all squared. Fits the difference of squares pattern, two terms, perfect squares that are being subtracted. There's our two factors. So they're identical binomials multiplied together with opposite signs. All right. So I know these patterns are quite complex, but you do need to give them a try, especially if you're going to be attempting some higher level math in the future. The difference of squares should be the easiest one to recognize, because when you're starting with two terms that are subtracted, if they are both perfect squares, then you can immediately get to a factored form. As far as the factoring perfect square trinomials are concerned, well, that again, you can use the pattern or you can use one of the other trinomial factoring techniques that you've already seen before. And hopefully this video will help explain the lesson notes as well.